Okay, today what I wanted to do on this one was an alternative method video. We have here an integral from the MIT Integration Bee 2025. We have the integral of x plus 1 e to the x ln x dx. Okay, I've done this one a little while back with just kind of a straightforward, pretty quick way, I believe. In this video, we'll do an alternative method that's probably going to take a little longer. What I want to do to start is I can just multiply it out and create two integrals out of this. So for the first one, we'll just distribute in the x. So we'll have x e to the x ln x. And then for the second one, we're just multiplying by 1. So we're just integrating e to the x ln x dx. And in the other video I think we just did integration by parts on this one. But here what we'll do is we'll do integration by parts on both of them using the DI method. So we'll kind of do side by side dueling integration by parts tables here. So we usually need to differentiate ln x, so we have at least that in both cases. We're going to differentiate ln x. Over here it's pretty simple, so we'll just integrate e to the x and we'll set it up like this. Over here we're going to group, we'll bring in this x here and differentiate this, and we'll integrate e to the x. Over here we'll go ahead, integrating e to the x, that's just going to be e to the x. Derivative here, that'll be just 1 over x. And then we'll stop here on this one. Over here, same kind of thing, integrate to e to the x. Derivative here, this is going to be product rules. So like derivative of x is going to be 1. So we're going to get ln x plus the second part, we keep the x. Derivative of this is going to be 1 over x. But then for this piece here, x times 1 over x, that's just going to be a 1. Let me clean that up. And then I'm going to keep going, just one more row. So if we integrate again, we get e to the x. Over here, that's going to be a 0. We differentiate this, we get 1 over x. So we get that similarity. That's why I'm doing it, to match them together. So then we'll go ahead, we'll have part of the solution on the diagonals. Because we're working these together, let's bring it all together. So so let's just start copying down. I guess we have, in every term, we've got e to the x. So let's factor that out, and we're going to have e to the x. We'll have this one, x ln x. It doesn't really matter which order I choose, I guess. So over here, we'll have an ln x. Here we'll have, let's distribute in the minus sign to this. So this will become minus ln x and then minus 1 right here. And then the last rows are going to be an integral. But this is the key part to the whole thing. The integral we're going to have in both cases is going to be this e to the x over x integral. Well, there's no solution to this in terms of standard functions. We can remember this is the exponential integral. So we could write this like e to the x for this thing. Now that would be kind of a problem, because if we end up with this in our solution, that's not going to match MIT's solution. I don't think they ever do that. I don't think MIT ever has their solution in terms of special functions. So what we'll do to capture this is we'll have minus, I guess I could go in the other order. We have minus the exponential integral here, and then we're adding it here. So we don't have to worry about any of this because they cancel off. So this is just a 0, and we don't have to be bothered with that. And so we're all set there. Again, we get more cancellation over here. ln x's cancel. And so for my final solution on this, we get just e to the x, x ln x, minus 1, add a plus c, and that's it. So I don't know, I wouldn't necessarily recommend it for speed, but at the same time, doing out all this crazy stuff didn't take a whole lot of time, so not that bad. But yeah, if you're on a timed exam, don't really do that. But yeah, if you're on the actual exam and you need to do this in 2 minutes, I probably wouldn't do that. Okay, that's it for today. Thanks everyone for watching. Have a good day.